how does our Earth get energy? What is the primary source of Earth's energy? Right? It's the sun, solar radiation. Right? What is solar radiation? Energy that comes on us from the sun. I can feel it on my skin. You probably learned in social studies class that earlier cultures totally respected the sun, solar radiation. Egyptians, they had a lot of sun gods, Ra, etc. The Greeks, Romans had Helios, Apollo, Sol, S-O-L was a Greek god. Right? And the sun can give off a whole wide range of wavelengths of energies. Everything from radio waves, infrared, which is heat, visible light, UV, gamma, X-rays. The sun gives off X-rays. And of all those different wavelengths, the one that it gives off the greatest amount of, the most, right, is light, right, which we're used to. Right? You ask a kindergartner, first grader, what does the sun give off? They're not going to say X-rays. Right? They're probably going to say light, because that is the greatest wavelength, the greatest amount, intensity that the sun will generate to us. Next definition is electromagnetic spectrum. You can copy the definition from the glossary or listen to the one I make up based on this poster. The electromagnetic spectrum is a wide range of wavelengths of energy. And it goes from low frequency, long wavelengths, like radio waves, to high frequency, lots of energy, short wavelengths, like X-rays and gamma rays. This is a poster of the electromagnetic spectrum. It is similar to the one on your reference tables. Actually, the one on the reference tables is flip-flopped, so the higher frequencies, like gamma rays and X-rays, are over on the left-hand side. That's the only real difference between the one on your reference tables and the one I have here. But I like this one. Just like reference table page 14, it just shows the only difference between radio waves and infrared or heat, UV, regular light, whether any type, color of the spectrum, X-rays, gamma rays. The only difference between them is the length of the waves of their energy. So if the waves are just a certain wavelength, our eyeballs are able to interpret that and see light. If it's a little bit longer wavelength than light, our eyeballs can't see it. We can feel it, call it infrared, heat. A little bit longer, not going to see that. Those are radio waves, but you can pick up those signals. Instead of the visible light wavelength that we can see, if it's shorter, we will not be able to see that necessarily, right? But we can sense that on our skin. It's ultraviolet. Even shorter, X-rays. Even tinier wavelengths, gamma rays, which we don't want to pick up these because they're higher frequency, more energy, more harmful. Insolation. Insolation comes from three words: incoming solar radiation. Now what I need you to do is I need you to take your pen or pencil and circle the part of each of these words that is pulled out to make insolation. Go ahead and do that. Hopefully you're circling the in incoming, the sol, remember that was like the Roman god Sol, he was the Titan god of the sun, and the ation from radiation, insolation. And the definition is, it's not all of the sun's energy, but it's the part that comes into us, makes it through the clouds, makes it through the atmosphere, and comes down to Earth's surface. That's the part that we receive, insolation. Good. Next we got to talk about the angle of insolation. That's the point where the sun is in the sky. How high up is it? What time of day is the angle of insolation low? Hopefully you guess sunrise, sunset. At the lowest, the angle of insolation will be 0. That's right when it's on the horizon, right as it's rising. You can see here already the sun has risen. It's above those trees, so it's definitely above 0. Maybe right now the angle is about 15 degrees above the horizon, a low angle of insolation. So we established when the sun is lowest in the sky, but when is it highest, right? When it is straight over our head, that special point straight above is called the zenith point. Pay attention to that Z word in your notes. When it's straight overhead, notice what the angle is. Look at my arms. The angle is a 90-degree right angle. Now, unfortunately, in New York State, we never get the sun at the zenith point. So what are we seeing? Right? As the angle increases, so does the intensity of the sun and the point that the sun is in the sky. So as the angle of the insolation goes up, so does the intensity of the insolation. Think about what kind of relationship that is, and in your notes, draw a line on the graph to show that kind of relationship. And therefore, there are some places, we said it's not New York State, but there are places that do have the noon sun at 90 degrees. That is the largest angle you can have. Straight above your head, that means they have the greatest intensity of insolation. That means they receive the maximum amount of solar energy. And if you want to see different places that have different angles of insolation, maybe not necessarily 90, you can either change your, increase or decrease your latitude to influence the angle of insolation. So change your latitude. Good. Next thing I'm going to ask you to do is look at the diagram of the Earth in your note packet. Right, notice that the North Pole is not straight up and down, but in fact it is tilted to the right, and in your diagram you have the sun's rays coming from the right. So I'm going to use this globe with the North Pole tilted towards the window, showing the sun shining on the right-hand side of the globe. First question, which latitude is going to have the sun at zenith directly straight overhead at noon on this particular day? Or who's going to get the sun's perpendicular rays? Look at those arrows coming in. Who do you think they're going to hit the strongest? I'm hoping you're going to look at a point not at the equator, but a place above the equator. Your answer is 23.5 degrees north. That's the answer to the first question. Now, if you can't see that, use this analogy. Look at all those sun rays coming at the Earth. Think of them like swimmers swimming a race, or runners running an Olympic race. How do you know who wins the race? Right? The person to cross the finish line, to touch the wall of the pool. Well, look at those rays. Who's going to win the race? Which ray is going to touch the Earth first? That's the one that's perpendicular. And if you look at your picture, 23.5 degrees north. Now, second question, what can you tell me about the intensity of the sun at the North Pole on this particular day? Well, your rays are not coming directly at the North Pole. My North Pole is not tilted right towards the window. So that means the angle is not as intense. The sun would be lower in the sky. So there's your second answer. And third, how would the intensity of the insolation compare at the equator on this day to the Tropic of Cancer? Well, we just established that the sun's perpendicular rays, the racers swimming the race, are going to touch the Tropic of Cancer first. Right, what that's telling us is the sun is directly overhead the Tropic of Cancer, so therefore it can't be straight overhead the equator, so the intensity must be lower at the equator, the sun must be lower in the sky. Alright, so if New York State never has the sun straight over their head, where do you have to go on the globe to find the sun at noon at the zenith point? Well, there's a bunch of different places. Right? On an equinox, you would go to the equator, 0 degrees. Can you read that? Summer solstice, for us in the northern hemisphere, first day of summer, right, in June, you would travel to the Tropic of Cancer, 23.5 degrees north. First day of winter, for us in the northern hemisphere, in December, you would travel to the Tropic of Capricorn, 23.5 degrees south. So different latitudes would have the sun overhead at different times of the year. Or basically, the other way of thinking about it is if I go from tropic to tropic, the middle of the globe, I call it the belly of the Earth, the tropics, those are the latitudes where they would have the sun directly overhead. And as we said, it's not just latitude that influences the angle of insolation, it's also time of day. So what time of day is the sun going to be highest in the sky? Good, noontime. Right? And remember, it's not necessarily straight overhead. Right now I'm shooting this at about noon on a September day, and the sun is up there in the sky. Right? It's not 90 degrees. It's pretty high up. Right? It's noontime, but it's September in New York State. Right? And then of course, when is the sun the lowest? We already shot that video. Right? Lowest in the sky, smallest angle, sunrise and sunset. Last vocab term is duration of insolation. A little bit longer word. It's the number of daylight hours that you have. The number of daylight hours is determined by the path of the sun across the sky. What is interesting about the path of the sun as it goes across the sky is the sun appears to move 15 degrees every hour. So that if you didn't have a clock, you didn't have a watch, you didn't have your phone, you could actually look at the angle of the sun, maybe use the sundial, and measure, and as soon as it has moved 15 degrees, you have known that now it is 1 hour later. So what we see is there is a relationship between the path that the sun takes across the sky. The longer the path, what's going to happen to the duration of insolation? Oh, it's going to be longer. Fill in the graph. What kind of relationship is that? And of course, if we have a greater duration of insolation, what's going to happen to the number of daylight hours? Well, that basically means the same thing. Greater duration, longer day. Fill in that graph.